Hi, welcome to Dissolve Chemistry. Let us continue our discussion on this thermodynamics with new topic, that is heat capacity. It is represented by letter C. So prior to going for detail with this particular topic, let us consider a simple experiment where we are taking two vessels of same weight of two different materials. Okay, one is aluminium, another one we will take it as stainless steel. Okay, now our experiment is that how much amount of heat energy is absorbed by the two different vessels between the temperature 25 degrees Celsius to 35 degrees Celsius. This you call it as T1, this you call it as T2. Assume that initially both are at 25 degrees Celsius and we want to raise their temperature by 25 to 35 degrees Celsius. Okay. So now what we will do, both we will keep it on the same magnitude of flame. Okay. So now what happens, so as you heat, by experience we know that the amount of the heat energy required to rise from 25 to 30 degrees Celsius for aluminum vessel will be greater than stainless steel. Means immediately it will get heated up, or its temperature will change from 25 to 30 degrees Celsius as compared to aluminium. What does this implies? That the amount of heat energy absorbed or withheld by a different substance is going to vary with substance to substance. Okay, some substance require more amount of energy, or it is having capacity to hold more amount of heat energy between the two temperature limits, and other will be having different amount. Okay, so now let us define this term. What do you mean by heat capacity? The amount of heat energy required to rise the temperature of the known weight of substance between the two limits of temperature. Two limits of temperature is called heat capacity. So therefore we will see mathematically how we define C is equal to amount of heat energy by delta T. So change in temperature means two limits of temperature will take T2 minus T1. We will define another term. Okay, so that we call it as what? Specific heat capacity. What do you mean by this? It is defined as the amount of heat energy required to rise the temperature of 1 gram of substance by 1 degree Celsius. Then it is called as what? Specific heat capacity, which is equal to Q by W into delta T, which is equal to Q by W is 1 gram and temperature raised will be 1 Kelvin or 1 degree Celsius. So therefore, so that will be equal to what? Amount of heat energy, or specific heat capacity we call. So that unit turns out to be specific heat capacity is equal to joule per Kelvin per mole per gram. Okay. Similarly, we will take one example to understand this. And one thing we should remember, this heat capacity of the substance is going to be an extensive property. Okay, that means the amount of heat energy held by the substance depends upon the mass of the substance. Now, as we have considered in the previous example, the vessel, if you take a larger vessel, okay, which is having larger mass, then if you want to change temperature from 25 to 35 degrees Celsius means you need more amount of energy. So therefore it is an extensive property. Now we will see one example. We will take the specific heat capacity of water is, say for example it is 4.18 joule per Kelvin per gram. Okay, so now we will see from this also we can confirm the heat capacity is an extensive property that we can understand. So now it is the 4.18 joule per Kelvin is the what amount of heat energy to rise temperature by 1 degree of 1 gram of substance. Now so for example, suppose if you take 180 gram of water, or you can consider 1 kg of water, anything you can consider, we will take this as 180 grams. So now what would be the amount of heat energy required to rise this one? So the amount of heat energy or heat capacity is equal to specific heat capacity into weight of the substance into what? Change in temperature. Consider 180 gram of water we will take, and we want to rise its temperature from, say for example, 25 to 100 degrees Celsius. Okay, so now we will substitute all in this equation. So therefore C is equal to heat capacity of water, that is 180 gram of water is equal to, so specific heat capacity, that is 4.18 joule per Kelvin per gram into weight of the substance is 180 gram we have taken into change in temperature 100 minus 25, so that turns out to be 75. So that we will calculate. So it turns out to be what? 4.18 joule per Kelvin per gram into 180 gram into 100 minus 25 is 75 Kelvin. You can take Kelvin per Kelvin get cancels, per gram gram get cancels. So therefore you will be getting heat capacity of 180 gram of water is equal to 4.18 into 180 into 75 joules. Okay, so this is simplify and you will get the answer. So therefore, so 1 gram of water, if you take, the amount of heat energy required will be different, and when you take 180 gram or 200 gram, whatever it is, means from this we can prove that it is an extensive property. Now we will talk about another type of heat capacity that we call it as what? Molar heat capacity. This molar heat capacity is very similar to that of your specific heat capacity. Okay, it is represented as CEM. See, molar heat capacity means it is the amount of heat energy required to rise the temperature of 1 mole of substance between 2 temperature limits. Okay, the substance taken will be 1 mole, right, into delta T. Okay, so therefore its unit turns out to be joule per Kelvin per mole. So this same molar heat capacity, when we want to define for a gaseous system, so then what will be its definition? It will be defined in 2 ways. That is, or it is going to vary under 2 conditions. At constant pressure it is different, and at constant volume is also it is different. So therefore let us define this molar heat capacity under those 2 conditions. So one we call it as what? At constant volume, molar heat capacity of the gas at constant volume, which is represented as Cv. Okay, and molar heat capacity at constant pressure, it is represented as Cp. Alright. So now assume that you have taken a 1 mole of gas in a closed container. 1 mole of gas in a closed container, and you want to bring the temperature from T1 to T2, and it is having internal energy initially U1. Now you supply energy in the form of heat. As we are supplying energy to as the system is closed one, so therefore heat supplied at constant volume we call QV we represent. Now what happens, it will absorb the heat energy and its temperature is going to change from T1 to T2. It means what happens, the internal energy of the system is going to change. Okay, it changes from U1 to U2. Apart from that, is there any change? Anyhow, we are not allowing this to do work because it is a closed vessel, constant volume we are carrying out. So therefore, whatever the heat is absorbed to bring that change in the temperature, that all is going to convert into internal energy of the system. So therefore, we will see that one. So now Cv is equal to Qv divided by delta T. Here delta T is T2 minus T1. So now Cv is equal to all the heat energy absorbed at constant volume will be converting into internal energy of the system, that we call the change in internal energy of the system, temperature. Okay, so this is what we call it as Cv, molar heat capacity at molar heat capacity at constant volume. Now let us talk about at constant pressure, molar heat capacity at constant pressure. See, so now you take a system or a container contained gas and fitted with weightless frictionless piston, and it contains 1 mole of gas. 1 mole of gas. Now, so your volume is not confined, it is allowed to change because we have to maintain the pressure constant. So here also same, we are going to change from T1 to T2, right? And its initial internal energy will be U1. So now what happens when you start heating this to bring the change from T1 to T2? So then what happens? It will absorb the heat energy, its internal energy will rise, followed by that what happens along with that. So there will be a rise, or it will do some expansion work. During the temperature change, we observe that there is a rise in piston, okay, or there is an expansion of the gas we are going to observe. So therefore, now the amount of energy absorbed will be in the form of heat is greater because it is doing certain amount of work also. So therefore, whatever the heat absorbed at constant pressure is called as Qp. Therefore, we will give Cp is equal to Qp by delta T. We know that from our previous discussion. If you have not watched, please go to the previous video where we have discussed in detail about a new term called enthalpy. So here the heat absorbed by the system at constant pressure is called change in enthalpy. So therefore delta H by delta T, okay, so that is nothing but your Cp, change in enthalpy we call, right? Now let us bring the relationship between Cp and Cv. See, for example, one thing you should remember, that always Cp for a given gas will be always greater than Cv. Okay, the reason is that here during the change in temperature it is also doing certain amount of work. Okay, so we will see the relationship between Cp and Cv now. Next topic, that is relationship between Cp and Cv. Okay, molar heat capacity at constant pressure, molar heat capacity at constant volume. So let us define Cp. Cp is equal to change in enthalpy with change in temperature. Okay. So we know that what is change in enthalpy we will give by as delta E is equal to P delta V or delta PV we will write. Okay. If you are not aware with this change in enthalpy, how we get this one, please watch our previous video where I have discussed, okay, regarding this enthalpy in more detail. Okay. So now let us substitute this in this equation. So then we will get Cp is equal to delta E plus delta PV by delta T. So we know that PV means PV is equal to RT. Right? We will substitute if it is not an expansion work. That in terms of change in temperature we can substitute. So then what it turns out to be, we will see that one. Okay. So because R is what? R is the amount of work done per degree rise in temperature by 1 mole of the gas. So therefore we will substitute RT into this in place of PV. So therefore delta E plus R into delta T divided by delta T, which turns out to be delta E by delta T, okay, plus R. So okay, delta T there, it will get cancelled and it will be there here. Okay, or if you want, we will write another step, delta T. These two will get cancelled. So therefore you will be getting, what is this term? This term is nothing but your what? CV. So therefore CV plus R. Cp is equal to CV plus R, or we can call it as what? Cp minus Cv is equal to R. Okay, and this is how we are going to bring the relationship between Cp and Cv. It means always remember molar heat capacity at constant volume, okay, is less than Cp by the amount R, or molar heat capacity at constant pressure is greater than molar heat capacity at constant volume by the factor R. That I hope you have understood the concept of molar heat capacity, specific heat capacity, and relationship between Cp and Cv. Thank you for watching. To watch more videos, please subscribe our channel. Thank you.